All right. Hey guys. Let's see. So, uh, welcome back. Today we're going to be doing some more operator theory, working on adjoints of operators, inverse of operators, things like that. If you haven't seen the other streams, that's perfectly fine. I'll try to review things as we go. We're still pretty early on into the material, so it isn't too complicated. Let's see. Other things I want to mention. Sorry for starting late, I guess. I want to start at 11, but I keep underestimating how much little technology things I need to go and adjust and tweak. So, yeah. And, yeah. So, yeah. Hi, Jaghead. I'm not sure how to pronounce that. Jaghead and the physicist Cuber. Nice. Is that cubing as in Rubik's Cubes? I have never really sat down to figure those things out. But yeah, I always have one, but I just twist it and turn it and don't really accomplish much. But yeah, okay. Let's see. Yeah, so things to mention for the week. See, I have a video that should be coming out this weekend, either Friday or maybe Monday or maybe even in the middle of the weekend. And this is going to be on divergent integrals and basically how we go about assigning values to those integrals and things like that. And so it's really good. That video is there to support the Fourier transform content that we have on the channel so far. And it's really interesting because, I mean, a lot of the Fourier transforms you want to make aren't actually well defined in terms of integrals. They are defined in terms of limits of integrals almost everywhere, and that's a major theorem in analysis. But just to mention how they come about when you don't have something that's actually integrable, well, we'll talk about things like the Cauchy principal value and things like that, and I'll give you a bunch of examples where the integrals really just don't work. And so it's pretty interesting. Cool. Yeah. Rubik's cubes. Yeah, they're fun. One day I'll figure out how to actually manage them. Let's see. Okay, so let's go ahead and hop over to the. Let's see. There you go. So we'll hop over here, and oh, I forgot to assign the screen to this. Let's see. See all these technology things I keep forgetting. All right, hang on. Boom, boom, boom. So what's neat with these with the tablet, it makes it really convenient, is that if you have your tablet connected or your iPad connected to your Mac with the a USB-C, you can start up a QuickTime Player and tell it to capture video from the iPad screen if things are working out as they should. And it helps if I actually plug the tablet in. Let's see. I always feel so disorganized with this. There we go. Boop. And okay, there we go. And bring it into OBS. QuickTime. There we go. Okay. Okay, and I think the bounds are all fit. Yep. Okay, cool. All right, so we've been talking about bounded operators and operators in general, and we'll get to the adjoint definition in a second, but let's just review some of the things that we've been talking about. So I'm not going to do a full-throated review here. That'll take a bit longer, but we've been talking about Hilbert spaces. And so these are vector spaces, say we can say complete, normed vector spaces with inner products. And those inner products look something like this, F and G, and they have this is our inner product. It's a complex value usually, and you have these sort of nice things like if alpha and beta are scalars and F, G, and H are inside your Hilbert space, then you have this sort of linearity property here. and beta GH, etc. And then you also have F and G is equal to GF bar, where the bar is a complex conjugate. Okay, so we have basically it's the inner product. I guess the last definition would be F and F bigger than or equal to 0 unless F is I say F is bigger than 0 unless F is equal to 0, then F inner product with F is equal to 0. And this is what allows us to define the norm of F as the square root of F inner product with F. It's janky, but that's the idea. So that's a Hilbert space, and that's the inner product. And we've been talking about these things that are called bounded operators and also bounded linear functionals. But they essentially, bounded linear functional is something that maps from T to H, from H to C. This is what we call a functional. And then otherwise, operators we usually denote as like A or B, or mappings between H and itself, say, or maybe even another Hilbert space, but we're just staying to ourselves right now. And so this is what we're going to call an operator. And in both cases, we say that they're bounded if AF is less than or equal to some constant C times the norm of F. And this, you can put the same definition for TF in this case, for absolute values, is less than or equal to C times the norm of F. And so basically these are exactly the continuous linear, I guess, and we're also going to assume linear, I should say, assumed. There are nonlinear operators, but we're not really talking about them right now. But basically, if these are linear and they satisfy these inequalities, then we say that these operators are bounded. And so this is what we're running with. And there's one other thing we should say about linear functionals before we run on, and that is the Riesz theorem. And basically it says that if T mapping from H to C is a bounded linear functional, then we say then there exists some G inside of our Hilbert space H such that we have that TF such that TF is equal to F inner product with G. And so this is extremely important because a lot of times your dual space or the space of bounded linear functionals on your norm vector space tends to be larger than the original space itself. And so in this case, though, we see that there's a direct identification between T and H, and we should also mention that this is uniquely defined. And so there's a unique G inside of our space that does this. And so this is a really nice theorem from Hilbert space theory. And we're always assuming here, for the sake of these lectures until I say otherwise, that we're working with Hilbert spaces. There is an equivalent version of the Riesz theorem for basically Banach spaces and like the space of continuous functions. And so if you're talking about continuous functions on the real line, then the Riesz theorem actually will give you a measure that corresponds to your bounded linear functional. And in fact, you can build a measure theory from functional analysis using functional analysis as your sort of building blocks to make measure theory. So, or you can go the other way around, start with measure theory and build a lot of stuff out of functional analysis. And so there's not really, you can start in either place. I personally enjoy functional analysis a lot more than I do measure theory, which is, which gets to be really complicated sometimes. Cool. Does anybody have any questions before we move on and start proving more, defining more things? Yeah, physicists. Yep. I have the habit of doing this out of the first argument. I have taken a few quantum mechanics courses, and I had to learn the other way around. But you're in Math Town now, buddy. So we are doing linear in the first variable. All right. So let's go ahead and talk about adjoints. So what we're going to do is we're going to let say A map from some subset of H to H, and we're going to say be a densely defined operator, linear operator. All right, and so we're going to start with that. So here I'm saying densely defined. That means that the domain that we're mapping from, which is a subset of H, I should say not D of H, but this corresponds to A. And we're basically going to declare that this is dense inside of H. So you can approximate anything in H with something in here. So in a lot of cases, your densely defined set could be something like the collection of continuous functions or test functions inside of L2, or it could be polynomials inside of the Hardy space or the Fock space. These are all great candidates for densely definedness for a lot of the operators that we often work with. But here we're just saying it's dense, so we can approximate other things with it. This means that I'm not thinking of A as necessarily being a continuous operator or a bounded operator, but I'm taking this consideration just because I'd like to have a more general version of the adjoint, so we don't have to come back and define it again. All right, so okay, so how is there a representation theorem on arbitrary Banach spaces? What they would look like? Okay, so yeah, so maybe I spoke too soon when I said that there's Riesz theorem for all of Banach spaces, but there's certainly Riesz theorems for particular Banach spaces. So for continuous functions, the dual space or the space of continuous linear functionals corresponds to measures, and then if you're in LP, which is a set of equivalence classes of functions that differ almost everywhere and have bounded LP norm, then in that case you get an LQ, another Lebesgue space, as your dual space, and the relationship between P and Q are 1 over P plus 1 over Q is equal to 1. And you can go and find a lot of these sort of correspondences as you go. The one for the measures is called the Riesz theorem, as well as the one for the Hilbert spaces. And I think there's a couple other spaces where there might also be called the Riesz theorem there too. But yeah, I'm sorry if I made any confusion there with some of my statements. But yeah, that's how it goes. But yeah, dual spaces can get to be very weird looking, and then sometimes you even take dual spaces of dual spaces, and those can be pretty weird. What's nice about the dual spaces of dual spaces, though, is that you have an embedding of the original space inside of the dual, and so you can even use that to achieve like a completion of the rational numbers if you build stuff up from the rational numbers and use that as your field that you're working with. And so outside of the the Cauchy completion or Dedekind cuts or something like that, you can actually build the real numbers using the dual of the dual, which is interesting. In any case, so let's get back to the adjoints. So we're going to let A be a densely defined linear operator, and we're going to define first a set. So we're going to define this guy dA star, which is the domain that we're going to be working over. And we're going to define this to be this collection of F inside of H such that the mapping, G inside of H, such that the mapping of that takes F to AF G is a linear functional, a bounded linear functional. All right, and so what that means then is that there is going to exist, let's say, how do I organize this? All right, so what this means, thus, there exists a unique, I'll say capital G, inside of H, such that AFG is equal to F against capital G, and we define A star going from this domain dA star to H as A star acting on little g is equal to big G. And so that's how you end up getting that. And this big G is unique, and because of the Riesz representation theorem, and so therefore this mapping, this A star as adjoint, is uniquely defined as well. Okay, so that means, yeah, so then I guess on well-defined I don't really have much to say. I put a mark there because I wanted to mention it, but really it comes from, the well-definedness comes from the Riesz theorem. So A star is well-defined by the Riesz theorem. And let's see, another thing is we can show A star is linear. On its domain, dA star. And that really just comes down to this. So if we take A star acting on alpha G1 plus beta G2 for G1 and G2 inside the domain. Then if this was interproducted against F, which is also in dA, then what do we end up getting? Well, let's see. So we know on one hand that alpha G1 plus beta G2 interproduct with A, F. We can move this A over. So I can move this guy over to here by just the definition that we have back over here. So so if we take a look at this, what this guy says is that AFG is equal to F A star little g, right? Because we defined A star little g to be equal to big G. And so then what we have is we can use the linearity in our first argument. Sorry, Mr. Cuber. And we get alpha G1 AF plus beta G2 AF here. And then let's move this over here. And then let me move some stuff out of the way. Boom. So we can see stuff. Don't see chat. Move chat up. There. And so what we end up getting is we have this. We can move A back over. So we have alpha A star G1 F plus beta A star G2 F. And tablet being sensitive. And then we end up getting alpha A star G1 plus beta A star G2, both against F. And so then therefore, since this holds for F, a dense collection of F's inside of H, this means, so then dA dense in H implies that A star alpha G1 plus beta G2 is equal to alpha A star G1 plus beta A star G2. Okay. And so, yeah, it's not a very complicated theorem, but I just want to kind of get you used to the idea of how to prove these things and navigate these sort of things. And we should also note that A star star, we should say if, well, I guess we'll make a statement about A star star in a second in the case of boundedness. All right, let's see. So I think there's a few chats I missed. So Physics Cuber is asking, though, would you be able to use a double dual to construct a completion of arbitrary norm spaces? Yes. Often when we're working with, so basically what you get is the dual space is going to become a complete vector space itself. So if you start with something that's not a complete vector space, then taking the dual of that should give you a complete space. And the embedding of the original space inside the dual of the dual, that would end up being completed in that case. All right, so a really nice way to view the adjoint of an operator is via graphs. The graph of to obtain the graph of A star from the graph of A, you just take the orthogonal complement and perform one additional reflection. Yeah. Okay. Yeah, I can see that. That would be a good way to go about this. I guess maybe I'm just a little bit more mechanical. This is sort of like how I've always gone about it in my life. But graphs are also really important when you are talking about operator theory too. You have the closed graph theorem, which basically tells you that if you have a closed operator, which means that the graph itself is a closed subset of H cross H, then if it is also defined everywhere, then it forces the operator to be a bounded operator, which is nice. So we can talk about that in maybe a week or so. But yeah, it's a very valuable theorem. We're just not getting to that yet. So maybe we'll talk more about graphs later, and maybe we can address some of the things you're mentioning here, maybe in a week or two or something like that. Okay, so let's see. All right, so we established a couple properties. The A star is well defined. That just follows by the Rees theorem. A star is linear, and that just comes from basically using the definition of the adjoint, and basically you start with this, and the idea is that you're going to turn this into this guy, and you want to use the fact that this holds for a dense collection of Fs. And because of that, that means that it's going to work for all. Basically, that's an identification between here and here. And so what we do is we take A star, we move it over, then we use linearity of the inner product, and then we move A star back over in this setting, and then we use linearity to put everything back together, and then not too bad. Okay. So that's adjoints, but it's often we really care about adjoints of bounded operators, and for at least the next couple weeks, we're just going to talk about bounded operators. Eventually, we'll get to things like Schrödinger equations, Fock spaces, and things like that for densely defined cases. And I'll give you an example or two here, but for a lot of things that we're going to want to talk about, and in particular for the spectral theorem, for at least the first couple of versions, we're going to be talking about these in the setting of bounded operators. All right, so a question from Tulip A. Branca. I have a question that may or may not be considered a silly question. A PhD math is capable to solve all the Putnam math tests, and no, absolutely not. Those are challenging questions, and honestly, I'm really crap at like contest level math. It's a very particular skill set that you develop, and it's not necessarily the same skill set you develop to do research in mathematics and sort of dive into a lot of these sort of deeper things. A lot of the Putnam questions and a lot of the Olympiad questions, those really just come down to like just knowing the right collection of tools to answer them quickly. They're not meant to be problems that you consider for a long period of time. They're meant to be solved, in a few hours. And so it's just a different skill set. And no, I've known a few professional mathematicians who did participate in the Olympiads. Some did well, some did sort of mediocre, but they went on to have successful careers without contest level preparation. Let's see. All right. So let's talk about this guy. So L of H here, I didn't put in our little review, but it is basically the collection of all bounded linear operators on the Hilbert space. And then A star is bounded. So if A is bounded, then we want to prove that A star is bounded. And we also want to prove that A star star is equal to A. A star star equals A really just comes down to the Reese theorem itself again. And so let's see. Okay, so a couple of things we need to establish. All right, so first, in order to define A star star, we needed to show that in the case of A being bounded, so we need for A being in L of H, that d A star, which we defined earlier, is densely defined. In this case, we're actually going to show that d A star is actually all of H. And so, and that happens because of boundedness. And once we do that, then we know that the adjoint is well defined. And once the adjoint of the adjoint is well defined, and once the adjoint of the adjoint is defined at all, the Reese theorem just tells us it has to be A, just by how it was defined. And so basically what we do is we're going to say consider some G inside of H. And the map of that takes F to F inner product with G, or AF inner product with G, right? According to our definition. Okay, so what we're going to do then is we're going to show that this is a bounded linear transformation, and so or linear functional. So what we're going to do is start with AF inner product with G in absolute values. This is a complex number, and our goal is to show that there is some constant C that we want. Ultimately, we want to have C times the norm of F here, where C is some number, and that number in particular is going to involve the norm of A and the norm of G. And so then basically, so we start with the Cauchy-Schwarz inequality. So this is bounded by, let's see, AF, and then the norm of G. And then the norm of AF is the norm of A times the norm of F times the norm of G. Right, so this second one is comes from the boundedness of A, and essentially this inequality is just from the norm of A. So norm of A is meant to be the smallest C for which this inequality holds, and so this is where that comes from. And so then this we can just reorganize things. We get norm of A times norm of G, and this times the norm of F, and so this here is RC that is greater than 0. And so therefore G itself is inside of A star, this domain, and but G was arbitrary from H, and so that tells us that H is a subset of D A star, which itself is defined to be a subset of H. So that means that D A star is equal to H. And hence, that domain is densely defined. Once that domain is densely defined, that means that thus A star star is well defined. Is well defined, and the Reese theorem tells us that A star star is equal to A. And that's by the uniqueness portion of that. Contest problems thrown at me for a stream. Oh, that'd be intimidating. It's scary enough just doing things that are routine. I have to like go and prep and like do things beforehand, just like a lecture, I guess. But yeah, that would be a bit terrifying. All right, and yeah, it'd be nuts. Again, I'm not good at contest problems. Don't ask me contest problems. You'll terrify me. It's a lot of like geometry and old school type stuff too. Like stuff I haven't really looked at in a long time. Like a calculus problem, differential equations problem, I'm cool with that. I teach those classes all the time. But yeah. Though I have been reading up on Hypatia and a bunch of like older mathematicians and stuff like that. It's really fascinating. It's gotten me to look into geometry a little bit more recently. There's a book called Elementary Geometry from Advanced Standpoint, and that's a pretty cool textbook that basically builds up like classical geometry in the context of how mathematicians sort of think today, and in terms of set theory and all that stuff. It's a great book. But yeah, but a lot of the stuff that you see in those problems that not really stuff that I do a whole lot. Okay, let's see. All right, so thus far we've demonstrated here that we have well-definedness of A star star. So that's great. What we want to do now is we want to show that we actually have boundedness. So we know that A star star is well defined, and that's going to allow us to show that A star itself is bounded. So let's do that. Alternatively, now that I've shown the domain is the entire thing, I could try to show that A is closed, and if I show that it's closed, then from closed we would get it from the closed graph theorem, but we don't have the closed graph theorem right now, and so we're going to do the next best thing and just, well, show it directly. It's not that hard. So let's go ahead and take a look. So we want to show that, so our claim is that A star is bounded. All right, so what do we got? We're going to consider this guy, the norm of A star F squared. I put squared there because I'm going to appeal to the inner product, and I don't want to write square root everywhere. So this is going to be less than or equal to the inner product of A star F, A star F, and then from here, I mean, you could say this is absolute values, but it's positive real anyway, just by our definition of inner product. Then we can have this by the Cauchy-Schwarz inequality. Oh, actually not yet. Then what we're going to do is we're going to use this thing that we just established, is that the adjoint of the adjoint is original A. And so what we end up having is this. This becomes A star F, inner product with A star F, with F now, because I moved over that A star. And now I can use the Cauchy-Schwarz inequality to get A star F times nor of A. All right, so what I did is I converted this problem of A star F's norm, and we want to basically show that we can have a bound on A star F's norm, and I converted it into this inner product problem. Through this inner product problem, we were able to use the only real thing we know about adjoints, in that we can sort of move them over. And so we end up getting this. And so now that this is established, we can go ahead and take a look at this guy And the what I can use here is the boundedness of A. And so I have this. This is less than or equal to the norm of A times the norm of A star F times, that wasn't A there, this should have been F, times F. And now, if you look on the left-hand side, we have a term squared. And if you look on the right-hand side, we have the term there. So this guy cancels this guy. And so we end up getting the norm of A star F is less than or equal to the norm of A times F. And hence, that implies that A star is bounded. And the norm of A star is less than or equal to the norm of A. But by symmetry, this also tells us that the norm of A is less than or equal to the norm of A star, because we know that they are sort of their adjoints of each other. And so then that tells us that the norm of A star is equal to the norm of A. It's a really handy idea. So that's adjoints for you. Some basic ideas about them. So first of all, how they're defined, and that comes from defining that that term, basically giving that definition that we had a little bit ago here. So we've defined what an adjoint is, and we have a definition through its domain, and the Ries's theorem gave us this. We have now established linearity, well-definedness, and from here we have also shown that if A has additional structure, like it is bounded, for instance, then it turns out that A star also inherits that structure. So A star becomes bounded. The adjoint of A star is just A, and ultimately they have the same norm, which is nice. Okay, so that's going to help us navigate a lot of things later, especially when we get closer into spectral theory. So some things that we can start talking about. So if you remember the Fock space, I'm going to talk about what adjoints look like on the Fock space. So the Fock space is some of these. It's one of these manifestations of quantum mechanics that arise from the Stone-Weierstrass theorem. And there is a operation that takes you from L2 of the real line, and it maps you directly into the Fock space, and that is called the Bargmann transform. And so you're able to transport things like the raising and lowering operators of the quantum harmonic oscillator, and you can bring it over to the Fock space, where it becomes actually these guys. The differentiation, it corresponds to the lowering operator, and should not be x, that should be z. And the raising operator becomes mz, and your Hermite functions are mapped from L2 into just powers of z. And so that's pretty nice. And so there's a whole textbook. So I didn't do a lot of work on the Fock space in the context of physics. I basically just I took physics class on the side while I was also working on this from the standpoint of complex analysis. So the space got a lot of development from various sides, where you have Fock, who introduced the space in the context of quantum mechanics, but then you had people like Bargmann and Siegel working on it from the complex analysis angle. So it turns out all the functions inside the space happen to be complex entire functions. And so there's a lot of nice interactions that you can get between the operators over the space and also the complex analysis bits of it. So let's take a look. So let's just review what the Fock space is. So the Fock space, F2 of C. There's a few ways to define this. I'm just going to use a power series definition. So F of Z is equal to AN times Z to the N, such that you have the sum of AN squared times N factorial is less than infinity. And so in this case, so here we have an orthonormal basis of z to the n over the square root of n factorial. And so that is z to the n normalized inside of our Hilbert space. So that so this term here, let's just call it en of z, is actually of norm 1. And so yeah. And so that's what you get. All right. So now now we have seen before when we talked about this that the differentiation isn't actually a bounded operator. So if we take a look at d dz of, say, z to the n, well, that's going to give you n factorial times e to the n minus 1. And the norm of n factorial times z to the n minus 1 is equal to, sorry, not n factorial. Oh, geez. That's not how differentiation works. I swear I teach these classes. N, I was thinking about n factorials from the others. You get n times z to the n minus 1. And so you get n times the square root of n minus 1 factorial. And yeah, and that's is equal to the square root of n times the square root of n factorial, which is equal to the square root of n times the norm of z to the n. And so hence the norm of d zn is equal to the norm of the derivative of z to the n is equal to square root of n times the norm of z to the n. And so I can make that n as large as I want, so there's no uniform bound for all of this. And so since n square root of n can be arbitrarily large, that means that d dz is not bounded. Okay, so it's not a continuous operator on the space. Okay, so but it is densely defined. So for any, it might not be. So we know that the Fock space, just from the fact that z to the n over n, the square root of n factorial, is an orthonormal basis, that means that any finite linear combinations of these n terms is still in the Fock space, which means then that polynomials are inside that Fock space. And so, yeah, so polys are a subset of F2 of C, and d dz of polys is a subset of polys, and so that implies that d dz, basically mapping from polys to the Fock space, is densely defined because the polynomials form a dense set as an orthonormal basis, since they contain the orthonormal basis. So that means that it satisfies everything we need in order to have for the adjoint to be well defined and exist. So now we know that adjoint exists. Now we need to figure out what it is. So I guess do the annoying thing. I need to figure out a better format for all this stuff so that I can stop moving my head around. Anyway, I also want to make the text as big as possible for people, especially if you're like on a tablet or a cell phone watching this. Then it'd be easier to see. But I don't know. I'm new to the streaming thing, so I'm still trying to figure things out. YouTube videos, you have so much control. You can cut things out, you can chop it up, you can increase the volume, decrease the volume, you can recover a lot. If the audio is sort of off sync, you can fix that right there. And all of that is done over like 20 hours before anything's posted. Streaming is like so much more, you have to be on the spot, just like in teaching. So to some extent, I'm used to doing this sort of thing, but just not doing this with the added baggage of all this technology. So, like, look how janky my little chat box here is on screen. I want to make sure it's there so that it is recorded, so that when you watch it later, if there's anything I need to edit or tweak, or like cut or anything else like that, then you still have this synced up and in there. Yeah, I guess this is all unnecessary to talk about, but I don't know. I've been surprised at how different it is doing streaming than it over, just basically making a YouTube video. All right, so let's go ahead and take a look at the next thing, and I wanted to figure out what is the adjoint of DD star. So what is the adjoint of DDX or DDZ? All right, so here we're going to appeal to the inner product. So if f is equal to the sum of a n z to the n, and we have g is equal to the sum of b n z to the n, then we end up getting the inner product between f and g. F and g is equal to the sum of a n b n bar divided by n factorial. Pretty sure that's right. Oh, let me think about this for a second. Yeah, that should be fine. If it's not, I guess it'll show up later, and then I'll have to apologize on stream, and I can't edit or cut, so maybe it's nice I preface with that. Anyway, so let's start taking a look and seeing what the adjoint is actually going to look like then. So let's take a look at DDZ of, say, a polynomial. So I'm just going to say z to the n. And we'll assume that g is in our space. The adjoint could also be, the adjoint of g, the domain of the adjoint could also be polynomials, and that would keep everything nice and compact. So g could also be a polynomial, if you like. So then this ends up giving us n minus 1, or n times z to the n minus 1 against g. And ultimately, what that is going to end up being is n times gn minus, say, bn minus 1 divided by n minus 1 factorial. Is this how I want to go about this? This is something I thought I could do off the top of my head, and maybe it was a little bit ambitious. Let's see. Okay, so let's take a look at another way to look at this. So my claim is that this should be, the adjoint should be multiplication by z. So let's take a look and see what you get when you have z to the n times z g. And if these give you the same answers, then that does identify the adjoint. So if we take a look at this, then we're going to have the inner product of z to the n times the sum of bn times z to the n plus 1. And let's see. So then if I want to rectify this, that sum, I get z to the n, I get the sum of bn minus 1 times z to the n. And so here we end up getting the inner product between z to the n and this one, and that is going to be bn minus 1 divided by n factorial. And yeah. I'm thinking I might have made a mistake somewhere. Hang on. Yeah, so I think up here. Yeah, that's what it was. I wasn't thinking. Yeah, so this needed to be adjusted. AN times BN bar times n factorial is how that comes about. And then that would make this n minus 1 factorial, which makes that bn minus 1 times n factorial. And then this one would have then been this times n factorial. Good. All right, so we see that d dz of z to the n against g is equal to z to the n with multiplication by z against g. And since this basically agrees on our orthonormal basis, and and basically that gives us what we want, that d dz is equal to the adjoint of d dz is multiplication by z. Okay, so that's pretty nice. So that gives us our first sort of non-trivial example of an adjoint. And this comes in handy in quantum mechanics and as an example for the quantum harmonic oscillator. Okay, so but that's over the Fock space, and if we change the space, we change the adjoint, because once you change the space, you change the inner product, and with the change of the inner product, the interactions with the inner product change. And so the adjoint is something that very much depends on your Hilbert space and the inner product space that you choose. And so then if you're going to move to a new Hilbert space, even when you're looking at something that should on the face of it be the same operator, the adjoint of that operator is going to change. It gets sort of, the image gets distorted through here. So if we take a look at this one, at the Hardy space, the space that sort of is a subtle change from the Fock space, where basically we just change the inner product, but then that changes the functions that are allowable and a lot of other things. So the Fock space is a set of entire functions, so they're well defined over the entire complex plane. But the Hardy space is defined on only the disk, and so it's a much smaller set. And so so here we have, say, the Hardy space H2 of D, and if you remember, this is a set of functions. Let's define the power series of an times z to the n, and in this case we're saying that the sum of an squared is less than infinity. Okay, and so here multiplication by z is bounded, so we don't have to worry about any domain restrictions. And so and then the question, and essentially it is the shift operator. Now, if I want to go ahead and consider the adjoint of this operator, then we can go ahead and do that. And so we're going to say, take a look at mz against f and g, and what we're going to end up getting is this. Let's spell it out. So we have multiplication by z, so we get sum of an times z to the n, inner producted with the sum of bn z to the n. Let's shrink this down a little bit, keep it visible, and this should be n plus 1 because we're multiplying by z. And so rectifying things again, we end up having the sum of an minus 1 z to the n with the sum of bn z to the n, And this starts, by the way, at n equals 0 to infinity, n equals 0 to infinity. This is going from n equals 0 to infinity, n equals 0 to infinity. All right. All right. Is that 1? No. 0 to infinity. No. 1 to infinity. Because we've multiplied by z and we shifted everything around. Okay. So what we end up getting then, so the inner product is, the Hardy space is really just the sum of the products of the individual terms. So we have the sum n equals 1 now to infinity of an minus 1 times bn. Okay. So now we want to see if we can figure out another way of representing this. And there's this other operation where if we basically take the operation, I'm going to call it just b right now, we end up getting this. So we take a look at this, b of g of z, and it's going to be defined as g of z minus g of 0 divided by z. And it's going to turn out that this is actually the adjoint, and we can go ahead and verify that just by going through and doing this sort of tedious process of working through the inner product. So let's consider f against this now, b of g. All right, so what we end up having, if you take a look at what we get here for b of g, if we subtract off the first term, if we subtract off g of 0, that is b of 0. And so we end up just killing that first term. So we're going to have bn z to the n divided by z. And then if I divide by z, we're just going to put a minus 1 here. And I can shift everything forward. So this becomes bn plus 1 times z to the n equals 1 to infinity. Or n equals 0 to infinity. And so then if we take the inner product between f and bg, we end up having the sum of an times bn plus 1, n equals, say, 0 to infinity. And if I shift these guys over just a little bit to make, let's see, yeah. Sorry. And basically, all you really need to do is compare this guy with this guy. And if you do that, then you'll see that they are actually the same sum. So they start at a of 0, b of 1, and then etc. So we can just go ahead and write this out. So we have, so it's a0, b1 plus bar. I should have bars. Oh my god, I'm not having bars. There you go. B1 bar plus a1, b2 bar, etc. And that's exactly where this starts. A0, b1 bar plus a1, b2 bar, etc. And so then therefore we can see that mz of fg is equal to f bg, etc. And so then therefore they are the same, and so mz star is equal to b. Whew. So that is an adjoint. So in this case, we saw two things. We saw that mz star on the Fock space is d dz, but mz star on the Hardy space is just b, or what we call the backward shift. And so, yeah, that's the idea. So one way to think about a lot of the stuff with the multiplication by z is if we just think of these power series as just a really sequence vectors. Then we have a0, a1, a2, etc. And it's called a shift operator because this becomes suddenly 0, a1, a2, etc. And then if we apply b, then we have a0, a1, a2, etc. and this becomes A1, A2, etc. So it chops off the first term. So one thing to notice is that multiplication by z on the Hardy space doesn't actually change the norm of the vectors. It just moves them forward by 1. But the backward shift does, because it chops off that first term, which does contribute to the norm of the vector. We have, moreover, that if we have b acting on M2, we get the identity, but the other way around, MZB is not. And that's because it chops off that first term. And so basically we'd chop off A naught, and then we shift forward again. And so here we see we have only a one-sided inverse for this operator. Okay, so that brings us to inverses. Identity, the I operator here, I guess I haven't really defined it anywhere yet, is basically the operator, the operation that leaves the function alone. So if you apply the identity to an element inside of H, then it just gives you that element inside of H back. Okay. All right, so let's take a look and start talking about invertible operators. Looks like I already did some practice here. All right, let's get rid of this and we'll fill this back in. Hopefully I can remember how to do it. Okay, so let's talk about invertible operators and like what these are. So if we take a look at the definition of an invertible operator, we're going to say that a linear operator A in L of H is invertible if the inverse is itself inside of the set of bounded operators, and that if we have A times A inverse is the identity, and A inverse times A as being the identity. And so in this case, we wouldn't say that the multiplication by Z is actually invertible as by this definition, because it doesn't satisfy for both sides. But we would say that it is I think, right invertible or left invertible. I think left invertible because it has a left inverse. So, but it's not right invertible. So, but in the case where we do have an invertible operator, and so if we have P and Q both inverses of A, which inside of L of H, then it turns out that P is equal to Q. And that's actually a pretty straightforward thing to show. We just show that they do the same things to the functions, that P and Q both act on functions in the same way. And if that happens, well, P and Q are operators, and then that's basically the definition of an operator. So if we take a look at PAQ of F, that's probably the cleanest way to do this. On one hand, PAQ, if I just take a look at AQ and using associativity, I can put these around it, then end up having P times the identity times F. And since the identity leaves F alone, we have P times F. And so we see that PAQF is just the same as PF. But then we can also see that if we take PAQF here and put the parentheses around P and A, then I end up having the identity times Q times F. And so this is just Q times F. But PAQF is equal to PAQF, and so therefore PF is equal to QF. And so they are indeed the same operator. So then to put a little Halmos here, and there we go. So now we've established that P and Q are the same operators. And so at least we know whenever we mention inverses, we are talking about uniquely defined operators. Okay, so then let's prove one last thing, and then we'll wrap up the lesson for today. And then what we're going to try to lead into after this is we're going to go into the spectral theory. And so you can't have spectral theory well defined without having inverses defined first. And so so I'll be happy to get into talking about what the spectrum of operators are and all that next week. And then we can use the multiplication operator, the multiplication by z, to get one example of a full classification of different kinds of spectrum elements. So we'd have our point spectrum, we'd have our continuum spectrum, and all that stuff. But let's go ahead and see. So if A is invertible, then one thing we really need to know is this interaction with the inner product, and in particular with adjoints. And so let's go ahead and take a look at that. So if A is invertible, then A star inverse is the same as A inverse star. So what we're going to do then is we're going to start with this. We're going to let, and I should also say A is inside of L of H. And so here we're going to let F be inside of H. And let's say F and G inside of H. And consider let's see, what am I going to consider? We're going to have A times A star times A inverse star, and we want to show that this is ultimately the identity. And so then what we do is if we just take a look at it in this terms of this inner product, I'm going to show that this term here is just F. And so since F is selected arbitrarily, that means that this is basically going to be the identity. And we can know that it's the identified as the identity because G is also arbitrary. And so so then that means that this has to be that we'll have identification at the end. So it's going to give us A inverse star acting on F against AG. And then I'm going to move A inverse star over. So it's going to give us F against A inverse A against G. And so then this gives us F times IG, and so which tells us that A star A inverse star is equal to identity, and conversely, by symmetry, A inverse star A star is also the identity. So basically swap their order, but we can do all the same things here, so symmetry. And so therefore, by definition, A inverse star is the same as the inverse of A star, and so this follows by definition. And so here. Okay, and so with that, I think it's probably a good place to stop, just because it's been about an hour now, and I don't want to make this stream too long. And in that case, come back next time. We'll talk about spectrum, and yeah, watch out for a video that I put out next week. In any case, thank you so much for watching, and I hope you have a great day.